Welcome to the introduction of our work. Take a step back, rethinking the two stages in visual reasoning. You can find our project page along with the code linked here. Reasoning is a fundamental ability for embodied AI, but how to capture and embed logical and causal relations from perception remains unclear. Our motivation is to explore reasoning by mimicking how humans process information, leading to our two-stage framework. Humans process sensory data, like visual and auditory inputs, through different channels, while logical reasoning is handled uniformly by the cerebellar cortex. Our two-stage framework reflects this. The first stage is symbolization, where sensory inputs are transformed into symbolic representations. The second stage is reasoning, where logical processes are applied to these symbols. Each task has its own encoder for symbolization, but a single reasoner handles reasoning across tasks. This differs from previous end-to-end models, which often perform well on specific tasks, but tend to overfit and lack generalization. Our goal is not to excel at isolated tasks, but to create a versatile system with broader generalization power, mimicking human reasoning. This leads us to a key question. Should the encoder or the reasoner be shared across tasks? To answer this, we conducted experiments focusing on both stages. In the symbolization stage, we explored how deep the encoder should be for different tasks. For reasoning, we tested various network architectures to find the most effective framework. Our results show that, when using data from multiple domains, a single reasoner focusing purely on logical reasoning performs best. This insight is valuable not only for visual reasoning, but also for improving reasoning in large language models, LLMs, where clear separation of stages can enhance reasoning ability. Here's an overview of our two-stage framework. Each visual reasoning task has a task-specific encoder that symbolizes the input. These symbols are then processed by a shared one-for-all reasoner, which performs logical reasoning across tasks. Finally, task-specific heads generate the answers. To validate our hypothesis, we compared 4 designs. 1. Both separated, separate encoders and reasoners for each task. 2. Both shared encoders and reasoners across tasks. 3. Shared encoder only the encoder is shared. 4. Shared reasoner only the reasoner is shared. The shared reasoner only approach consistently outperformed the others, even matching the performance of ad hoc models, both separated, while offering better generalization and avoiding task-specific overfitting. We also explored the boundary between the symbolization and reasoning stages. Different tasks require different levels of symbolization. Through experiments varying the depth of the neural network, we observed that symbolization depth increases initially, but plateaus at a point, marking the end of symbolization. Different data sets require varying amounts of parameters to reach this boundary, depending on task complexity. For instance, Raven dataset images are simpler than the complex human-scene interactions in Vanguard HOI datasets. Next, we evaluated the best reasoning architecture under the shared reasoner-only framework. We tested various models, from lightweight ones to LLM-based reasoners, across 9 tasks. Surprisingly, a simple MLP-based reasoner showed strong performance, even rivaling state-of-the-art ad hoc models. In contrast, LLM-based reasoners didn't perform as well, suggesting that simpler models can be more effective for reasoning tasks. We also measured reasoning consistency. For the same problem, we asked different questions, e.g., what is the correct answer, and is a certain option correct? A good reasoning model should provide consistent answers. Our one-for-all model showed better consistency compared to task-specific models, further proving the strength of our framework. To test the reasoner's generalization ability, we used 5 cross-domain datasets. Training on an increasing number of domains, we observed improved performance on the target tasks, supporting the idea that the reasoner focuses on task-agnostic, pure reasoning, what we call the approximation principle. Finally, we analyzed reasoning in large language models, breaking the process into symbolization, conceptual understanding, and answer generation. Our findings show that while LLMs perform well in perception, they struggle with reasoning, especially in the Raven and Vanguard tasks. That concludes our presentation. If you're interested in learning more about our work, please scan the QR code to visit our project page. Thank you.